Welcome to part 5 of Robotic Arm Manipulation with Reinforcement Learning. In part 4, we wrote most of the agent class here, we already had a buffer and our networks defined. So in part 5, we're going to go ahead and finish the agent class and get started on the rest of main.py. So our last line of part 4 here was to call update network parameters. So we actually need to define that function. So let's go ahead and do def update network parameters. We're going to pass itself as always and a default tau of none. And we're just going to say if tau equals none, then tau equals self.tau. So basically if tau is not passed in, then just go ahead and use the tau defined for the class. There are probably a few other ways we could do that. We could have just defined a default tau, but this is how we're setting it up. Here we need to go ahead and get our params. So we're going to say actor params equals self.actor.named parameters. critic1 params equals self.critic1.named parameters. And in the same way, critic2 params equals self.critic2.named parameters. Target actor params equals self.targetActor.named parameters. Target critic1, because if you recall, we have 6 total networks. We've got our actor and dual critics, and then we've got a target for each one. So we're going to say critic1 params equals self.targetCritic1.named parameters, and target critic2 params equals self.targetCritic2.named parameters. Okay, we've got all of our name params. Now we need a state dictionary from each one. So I'm going to say critic1 state dict equals dict critic1 params. And we are going to copy and paste that for critic2. And then we'll do the same thing for actor state dict is a dictionary of actor params. And you'll see why we're doing this very shortly. Here, let's move these around just so they're in the same order as up above. Doesn't really matter, but it does look a little bit cleaner. So now we can say target actor state dict is a dictionary of target actor params. Target critic1 state dict is a dictionary of target critic1 params. And then again, we'll just copy and paste that for target critic2. And then we have all of our dictionaries. Now, we are going to use, so the reason we have a target network and a primary network is that it provides sort of a stable baseline for learning. Your primary network can be updated more often than the target network, and then the target network is that sort of stable, less frequently updated thing that we can use for learning. So there are a couple of different ways to do a target network update. Some algorithms call for just doing a direct parameter copy, which is of course simpler. Others have what is considered, and I'm going to mispronounce this, but Polyak averaging, which is closer to what we're about to do. So we're going to copy a portion of the parameter values over to the target networks. So for name in critic state1 dict, we're going to say critic state1 dict name equals tau, that's where that tau value comes in, times critic1 state dict name dot clone plus 1 minus tau times target critic1 state dict name dot clone. So let's think about what this is doing. If you have a value, and we'll simplify it quite a bit, but let's say you have your critic1 has a parameter value that's coming in at 50. So let's say critic1, and all this is throwaway code. You don't have to type it with me. So let's say critic1 is 50. 1 is 50, and then target critic1 is 40. So, and if our tau value was, let's say, 0.1 to keep things simple. So tau is 0.1. Then what that would end up doing is it's going to end up multiplying tau by critic state 1. So, tau 0.1 times 50. So that first value would become 5. So tau times 50 is 5. And then it's going to add that to 1 minus tau. So 0.9 times 40, which we'll just do is 36, equals 41. So what we effectively just did there, if the original value was 50 and the critic value was 40, we brought the critic value very slightly closer to, the target critic value very slightly closer to critic 1. So we're not necessarily directly copying. We're not doing a full, clone of the parameters. We are, for all of the parameters, bringing them slightly closer to the original network with a to the magnitude of the value of tau, if that makes sense. All right. So description over. We're going to go ahead and type out the rest of these. For name in critic state 2 critic 2 state dict. I was trying to type that incorrectly. And then this is going to look a lot like what we just did here. So I am going to copy and paste it. And then we'll just swap out critic 2, and then target critic 2. All right. So for critic 2, same thing, critic 2 state dict name, critic 2, and target critic 2. And then we will copy and paste one more time, and we're going to do actor state dict, and then again, actor state, and then we'll just type this one out. Actor critic target actor critic state dict. All right, and then a good thing to check is always, does anything look weird in what the editor is showing you? In this case, you'll notice that there are no values grayed out here, so everything was used. So that tells me that we did probably type everything out correctly. All right, and then finally, at this point, we have a state dictionary that has been averaged a little bit more towards, our targets have been averaged more towards the primary networks. So we can go ahead and say self.targetCritic1.loadStateDict and critic1, and then do the same for the others. Self.targetCritic2.loadStateDict, critic2, and self.targetActor.loadStateDict. And we're going to do an actor state dict. All right, so we have completed this section. Let's go ahead and we've just got some housekeeping functions to put together. Oh, you know what? I defined this earlier and I did not use it. So we're just going to delete that. And now we need to complete our housekeeping save models and load models functions. And these are going to be pretty simple. So if you recall, and this is where having methods in objects that allow them to perform functions on themselves can be very, very useful later. So if we come over to networks, if you recall, each network had a save checkpoint and a load checkpoint. Now there's no reason we couldn't have built this functionality outside of the network, but we would have had to, write one, we would have had to, interact with the parameters of each network separately. What this gives us, the fact that we've got that built in, is that now for save models, we can just say self.actor.loadCheckpoint and just do the same thing for each one. Self.targetActor.loadCheckpoint, self.critic1.loadCheckpoint, self.critic2.loadCheckpoint, and self.targetCritic1.loadCheckpoint, self.targetCritic2.loadCheckpoint. And I like to give myself a little bit of logging in this process. So you can do this a couple of different ways. You could stick a log statement after each one if you want to have it check and make sure that every single checkpoint was loaded individually. That can be useful for troubleshooting. Just in the at minimum though, I recommend having something that at least says, successfully loaded models. And you could even do, here, let's do it this way. We're going to do a try. We'll do that on the load. We're going to assume we don't want this on save, we want this on load. So we're going to assume that save always works, and if save ever fails, we do want that to error out. It's going to save fairly frequently. Down here, we're going to copy, I basically just wrote the wrong code in the wrong function, or right code in the wrong function. So all of these loads are going to be under load models. Back to save models, we are going to do something very similar. Self.actor.save checkpoint, self.target.actor.save checkpoint, self.critic1.save checkpoint, self.critic2.save checkpoint, self.targetCritic1.save checkpoint, and self.targetCritic2.save checkpoint. All right, now that I'm working in the right function for each one, this stays the same. That's good. Down here, we want to put this whole thing in a try-catch block. So let's talk about why. And I'm sure there are several ways to handle this. You could check to see, you could do something like an if file exists, then load, otherwise fail. I'm using this for simplicity. It works for my use case. I'm basically saying try to load all the networks. If you successfully load, print successfully loaded models with an except print failed to load models starting from scratch. And the reason we're doing this, both the overall just having a load models and then wrapping it in a try catch, you'll find that you end up running these things many times. It's not like you in a normal development cycle are going to build the code once, type it all out in one run, and then your model's going to work exactly the way you expect it to. Now, it may for you in this case, because, again, you're following a video on how to build this code, but that is not a normal development flow. So it's pretty normal to, have a model that you've saved, that, you started, you ran it for 3,000 iterations, you have a tweak you want to make, you stop the code, make your tweak, and then start it back up, and you want it to start from its last known state. So that is where we have a load models. All right. So at this point, our agent class here is done. So we're going to go ahead and come back over to our main Py and go ahead and start coding out the really the main training loop. So we're very close to being able to see this thing work. So we're going to set up alpha as we're going to get to some of our parameters here. And actually, let's call this, let's go look at our function here. So I think we said we switched this over to actor learning rate and critic learning rate. So we're going to say actor learning rate equals 0.01 or 001. That's what we're starting with. We'll do a critic learning rate also equal to 0.001. And we'll do a batch size of 128. A layer 1 size of 256. Let's see, layer 2 size of 128. So you might ask the question where I'm getting some of these parameters. And there are two different good ways to get parameters in reinforcement learning. One is you can go back to the original paper, and that will usually, most of these things started out as a research paper. The researchers are usually going to publish something in the appendix that shows you what params go into that network, and that is always a really good way to find at least a starting point. The other is through experimentation, and I'm going to make a video later in this series on running parametric experiments, basically allowing your code to cycle through and run with different parameters and find the thing that works most efficiently for your use case. So that's how I found these. They are a little bit lower than what was in the paper. If I recall correctly, it had something like 400, 300 for layer 1 and layer 2, and may have had the same batch size, but I landed on this through experimentation for solving this particular problem. All right, let's go ahead and we are going to call agent equals agent. Oh, we probably need to import agent. So let's come up here from TD3 Torch, import agent. Now we can call it. And lots of parameters. So actor learning rate equals actor learning rate. Critic learning rate equals critic learning rate. Tau equals 0.005. Input dims is going to be, we're going to pull a variable from our environment here. We're going to call this env.observation_space.shape. env equals env. So we're passing in the environment we built. n actions, so number of actions, is going to be another variable that that our Robosuite environment here gives us. Something important to note if you're doing this with another project, the gem wrapper is what's making many of these things work correctly. Out of the box, Robosuite will not give you, all of these parameters quite the way we expect them. You can do it, but you do end up having to do some changes and reshaping, and just using gem wrapper fixes a lot of the problem for you. That's really the cool thing about gem, is it is a standardized interface for working with these kinds of problems. All right, we're going to say layer 1 size equals layer 1 size. You can see I'm very boring with my variable names. You should always make these clear and easy to see, or easy to understand. Layer 2 size equals layer 2 size. And finally, batch size equals, you guessed it, batch size. All right. We are going to get into a little bit of our TensorBoard config now. So I'm going to say writer equals summary writer, and we'll give it the logs directory. N games is equal to, we'll do 10,000 is a good number. This will take a very long time. I'm running with a reasonably fast GPU locally. The nature of the environment, the nature of just how fast Robosuite can run, does tend to make this take a little bit longer than maybe learning on a classic Atari game or something like that. So just be aware, this could run for 10, 12 plus hours very easily. So best score, we're starting best score at 0. We're saying, and then episode. So this is something I like to do. I'm going to call this episode identifier. And what this should be, and you can absolutely change it, this should be an amalgamation of useful information. So I've talked a few times about how these things are almost always experiments. You're not going to run it with one set of parameters and then that set of parameters just never changes. You're going to play with various different things. So you can think of the episode identifier in this context as something that's going to show up over the TensorBoard logging section, and it's going to be what your results are labeled with. So we'll do an F to make that an F string. I'm going to start with index 0. I like to number them. It makes it easier for me. And then we're going to say actor learning rate equals actor learning rate. Critic learning rate equals critic learning rate. And we'll also do batch size. No, you know what? Let's do layer 1 size equals layer 1 size, and layer 2 size equals layer 2 size. All right. And what that's going to do is, as you experiment with different parameters, it's going to let you see which parameters worked better and which ones didn't work as well. And while it might seem obvious, like, hey, I just put these parameters in, of course I know what I ran that with. When you are 20 or 30 different training runs in, trying to figure out what worked and what didn't, this is where you do want to have a little bit more information available to you, especially when these things can run over days or weeks to run many different attempts. All right, here we're going to say models. We're basically just going to say agent.load models. If I could spell agent, that would be helpful. So this is going to try to load the models if it can. And then we start our training loop. So the training loop is going to be for I in range and games. Observation equals env.reset. And if you've worked with any gym environment, this is all going to look really familiar. So you always start with a env reset every single time. That's the first. It's resetting the environment. It's starting the game, so to speak, off. You're going to set done to false. You're going to set your score to 0. And then, while not done, play the game. Or in this case, tweak the robot arm. So that's going to be action equals agent.chooseAction. Observation. So this comes back over to, we built our agent. Our agent has a chooseAction class that is, or a chooseAction function that's going to pass, it's going to pass this into the actor network to pick an action, and then it's going to add some noise and finally spit that back out for us to take action. So that's what that's doing, agent choose action. We're going to actually use that action. So next observation, again, very standard for anything where you're doing in gym. Reward done info equals env.step action. And env.step is actually the thing that's saying, hey, go take the action you just produced and plug it into the environment and run it. We'll say score, add the reward, so plus equals reward. Agent.remember. So this is going to say observation, action, reward, next observation, done. And if you're curious about this set, we're getting a state or observation, the action, the reward, the next observation, and then whether or not we're done. It would be worth reading up on Markov decision processes. This is, again, this is pretty standard for these types of problems. I will not go over the theory here, but that is worth reading up on. And then we're going to say agent.learn. So every single step is going to take some action, and then it's going to store it in our buffer, and then it's going to go and attempt to learn from that observation, as long as the buffer is over batch size times 10. So I think we set our batch size to 128. So as soon as batch is over 1,280, it's going to go ahead and start attempting to learn and make improvements. All right, and then here we will do if writer.addScaler. So addScaler, this writer object, if you recall, is the summary writer from TensorBoard. So writer.addScaler is going to actually push our score out to our TensorBoard logs so we can see what's going on. So we're going to say score dash episode identifier, that's string that we built up above, and score and global step equals I. So that'll actually log something so we can go see what's going on. And then something I find useful, so we'll do if I percent 100, we'll do I percent 10, and we'll do agent.saveModels. So we're basically saying that every 10 epochs, every 10 iterations, we're going to go ahead and save the model so that we've got that. And then I also like to have just some logging here. So we're going to say episode, give ourselves a space, Actually, let's be consistent. I used f strings everywhere else. Let's use them here. So I'm going to say episode I score and score, and that'll just give us like a constant readout of the current episode and what its score was. So, all right, and I think with that, we are at a point where we can go ahead and run this and see what blows up. All right, so it didn't like layer 1 size. Let's go see where that problem popped up. So line 38 in module, so yep, right here. We said layer 1 size equals layer 1 size. So let's go over to our agent and see what we didn't like. Okay. So over in the main class, I did layer _1 size, and here I did just layer 1 size and layer 2 size with just the 1 underscore. So I'm just going to go ahead and standardize and say they're all, get rid of that other underscore for all of them. Keep it one variable name. All right. Take 2. Oh, I had one more instance of layer 1 size down here to fix. Variable names matter. And you'll see where this was useful. So we know that we didn't start with a model. We, failed to load models starting from scratch, and now we are getting our episode, our results here. So I mentioned earlier that we were logging some statistics. So let's go ahead and go take a look at what that gives you. So I am in my terminal, going to navigate to that project, and then I'll pull it back up. All right, so I have gone to my TD3 Robosuite door project here. And this is the same one that we were in earlier. So I'm going to call TensorBoard. Actually, I'm not going to try to remember the command. Control R is a wonderful shortcut in a Linux terminal. So you just start typing and right arrow for things that you've typed before. So that command is going to be TensorBoard --logdir equals logs, and then the port, in this case the default is 6006, but I like to set it explicitly so I can change it more easily later. And the reason this is logs is because we set our summary writer here to logs. So I'm going to go ahead and run this. And that's a normal error message. And you'll notice that it's started up a TensorBoard server here on localhost 6006. So if I control click on that, it's going to give me this screen. And for me, I'll always click on scalars here. And then this becomes a graph of your your training process, and it's a real-time graph that you can use to monitor how things are going. This smoothing section is really, really useful because there's a lot of noise in the data, or a lot of noise in the training results. If we go to no smoothing at all, we can see that we had a huge spike here just a little ways into training. But that doesn't really tell us how we're doing, overall. So I normally hang out somewhere in the low 90s. This little box here is fit domain to data. You'll want to hit that every so often. That expands it, and this one changes the scale on the left. So I'll usually use low 90s, and that gives me an idea of how how things are going as they go. What we should start to see here over time, normally around 1,000 or so epochs, you're going to start to see things wander upwards, and that will start to show you some decent training information. I'll see if I can find another one of these that's already pre-trained to give you an idea of what to look at or what to expect. All right, here's another one of mine. This was not part of the canned video, so we'll see what I have for data here. Okay, so it looks like this was probably a second training run of mine and doesn't really tell you what I was hoping for, which was to see something go, much, much better. But that does kind of show you where smoothing is useful. Like, this is just a bunch of data. This is something that makes, a little bit more sense. We can go ahead and look at here, 607, and I'll pull up logs from my door training. This was, again, the original project. And here's what you should expect it to look like. This was when I trained the door opening task from scratch. So we started down here, and you can kind of see that it had hit, it started, we can zoom in a little bit here. Well, maybe we can. So you can see that the first 100 or so, it was pretty low. It didn't really come up very much. And then you'll also notice some sort of wavy results here. So if you're still, 500, 600 epochs in, and you're seeing the model dive up and down, that's completely fine. What you're looking for is an overall trend upwards. And then coming back to our active training, we're still, you can see in that kind of that flatlining mode, what it should start to do is it should start to learn a little bit, and then we should start to see it slowly trend upwards. So I'm going to end the video here and let this sit and train for a while, and when we come back, we will talk about the test.py and maybe start to get into a little bit for parametric experiments and how you can use a parametric experiment to find the right parameters. So, all right, so right after I was about to stop the video there, I noticed some potential technical difficulties, and this is why you do want to graph things and look at them as you're training. You'll notice this one was kind of tanking. It just kind of flatlined, and at 240 it had not come back up. So that did help me find a bug, something that I mistyped, and you can go ahead and fix this in your implementation. So one of the core parts of the main training loop here is that we must set observation to next observation. So we need both of these values when we're storing them, but then when we get down here, we need to set current observation to what was originally next, and I did not have this line, and the network was just flatlining here. So if we look at my second run, and this is again where you can see it's useful to store these things. We are now at a score of 30 very, very quickly. You know, it should hopefully rise further. So with that, I'm going to end this video a second time and go to video 6 for the test script.